So this is Chapter 9 on alkynes, Part 1. Alkynes contain a triple bond, as you know. General formula is CnH2n-2, two elements of unsaturation for each triple bond. Some reactions resemble the reactions of alkenes, like the addition and oxidation reactions, and some reactions are specific to alkenes. In terms of nomenclature, you want to find the longest chain containing the triple bond, change ane to ine, as you all know. Number the chain starting at the end of the closest to the triple bond, and give branches or other substituents a number to locate their position. So, for example, here's but1-ine, a terminal alkyne, right? So it's in the one position because it's in between 1 and 2. This is but2-ine, and this is an internal alkyne in which the triple bond is in between two methyl groups. So you can tell whether it's a terminal alkyne when you have this acetylenic hydrogen. When you don't, it's an internal alkyne. All other functional groups except ethers and halides have high priority than alkynes. So, common names, that it's named as a substituted acetylene. So, for example, this would be the acetylene backbone. This would be methylacetylene or terminal alkyne. And this would be isobutyl isopropyl acetylene. So isobutyl, isopropyl acetylene, and this is an internal alkyne. So this is in terms of common name. Physical properties, they're nonpolar, they're insoluble in water, soluble to most organic solvents. Boiling points are similar to alkanes of the same size, they're less dense in water, and up to 4 carbons, they exist as gas at room temperature. Ethine. It's commonly called acetylene. It's used in welding torches. Oxyacetylene flame reaches temperatures as high as 2,800 degrees C, and they're thermodynamically unstable. When it decomposes to its elements, it releases approximately 234 kilojoules of energy per mole. Synthesis of acetylene from coal, you can take calcium carbide, which is coal, in the presence of water. This will generate the acetylene and calcium hydroxide. So you essentially heat coke with lime to form this calcium carbide, and then you just add water to the calcium carbide. You can also generate acetylene from natural gas. If you take 2 equivalents of methane at really high heats, you can generate acetylene with hydrogen. Molecular structure of acetylene, triple bonded carbons have an sp hybrid orbital. A sigma bond is formed between carbons by the overlap of sp orbitals. Here's your sigma bond. Sigma bonds to the hydrogens are formed over here by using the second sp orbital. Since sp orbitals are linear, acetylene will be a linear molecule. Each carbon in acetylene has 2 unhybridized p orbitals, one with 1 non-bonded electron. It's the overlap of the parallel p orbitals that form the triple bond, the 2 pi orbitals. So here are the 2 pi orbitals, and then you have the cylinder of electron density shown here. Bond lengths. So we already know CC bonds 1.5 angstroms, CC double bond 1.33, C triple bond C, it's less, 1.2. Also, in the terms of carbon hydrogen, you go from 1.09 to 1.08 to 1.06. So yes. Now acidity, so as you go from no degrees of saturation to 2 degrees of unsaturation. In the acetylene case, you're increasing the acidity of the molecule. So you go from a weak acid to a stronger acid, and the pKa is around 25 for acetylene. So versus 44 and versus 50 from the the unsaturated version. Terminal alkanes are more acidic than other hydrocarbons due to the higher S character of the sp hybridization. Terminal alkynes can be deprotonated quantitatively with strong bases, particularly with sodium amide. Hydroxides and alkoxides are not strong enough to deprotonate alkynes. So, if we wanted to form an acetylide ion, the first thing you can take to generate the amide is take ammonia. In the presence of sodium and iron catalyst, this will generate sodium amide and hydrogenous gas. Now you can use this to react sodium amide to the alkyne, and that will deprotonate this, right, to generate ammonia and just make this into sodium acetylate. This resulting acetylate is a really strong nucleophile. So because it's a really strong nucleophile, it can do substitution reactions. So that we're on the same page in terms of mechanisms, what needs to be done is the first step. You should draw an arrow, right? So that you generate sodium amide, and then also in this case, this will pluck off that hydrogen, bringing the electrons to the carbon, generating your sodium acetylate, which is right here. So if you use sodium acetylate, you can do SN2 reactions, right? So here's your acetylate, nucleophilic attack, displacement, all in one step, generating the internal alkyne. So one of the best methods for synthesizing substituted alkynes is nucleophilic attack on an unhindered alkyl halide. SN2 reacts with primary alkyl halides, and that would lengthen the alkyne chain, right? So it went from 1, 2, 3, 4 to now 1, 2, 3, 4, 5. Unhindered alkyl halides work better in an SN2 reaction, so you have this preferred over that. So you can have acetylide ions function as strong bases and perform elimination reactions. So if we look at this reaction, I'm going to just draw the isopropyl bromide a little bit differently. So here's H, right? Sorry, H and H, and then CBr, H, and then I'll just say CH3. Okay, so in terms of mechanism, when you're drawing this out, you have to draw the full mechanism where you have it pluck off, right, that hydrogen, and then kick out the bromide. So it happens all in one step. This is a concerted reaction, and remember, it has to be anticoplanar from our previous chapter, chapter 6, when we talked about elimination reactions and substitution reactions. This will then generate butylene, and then propene, and then bromine flying about. So let's do a problem. Show how to synthesize 3-decine from acetylene and any necessary alkyl halide. So what we want to do is we want to go from acetylene to this dec3-ine or 3-decine. First thing you want to do is subject it to NaNH2, and then react it with CH3CH2 5Br, so that'll give you the rest of the molecule so that you generate the octine, right? after you generate the octine, you're going to use sodium amide. Step 2, add the ethyl portion of it, right? So that you have this part of it, and now you want to add to here, and then you'll generate the 3-decine. You can have additions to carbonyl compounds in which you have a nucleophile attack carbonyls, right? This will then kick off the electrons to the oxygen so that you generate an alkoxide. You can take that alkoxide ion, protonate it from water so that you have this alcohol. So in general, nucleophiles can attack carbonyl compounds, forming an alkoxide ion that on protonation will form an alcohol. It's critical. If we look at mechanisms for alcohol formation using acetylide as your nucleophile, here goes your attack. Electrons get kicked off, generate the alkoxide in the presence of H3O, which it will draw out here. Sorry about this, you're going to have to bear with me here. I'm trying to draw the best hydronium ion as possible. Your electrons here will pluck off that hydrogen, quench, right, the oxygen, so that you generate the alcohol plus H2O. Again, make sure you show all, in mechanisms, all the arrows. You can also have addition to aldehydes in the same ways as before. You have nucleophilic attack, electrons to the oxygen, then in the presence of hydronium ion, you can pluck off that hydrogen. Again, I don't need to show that because I just showed it in the previous slide, so that you generate an alcohol, a secondary alcohol actually. So if we take, for example, 3-methylbutanone, add NaNH2, then you add phenyl aldehyde, right? In the presence of hydronium ion, you're going to have deprotonation here. This is then going to attack the PHCHO, which is essentially this molecule, which I'll try to draw very quickly. Here's your P, and then aldehyde here, sorry. So then that would add on to here, right? Kicking off, so let's say you already you deprotonated, right? So that hydrogen is no longer after first step 1. So here's your negative charge. Remember, electrons go up like this. So once you do that, you generate the alkoxide, which then gets protonated here to generate this. I'm just showing parts of the mechanism so that you can see it. This will generate secondary alcohols. You can also add to ketones, right? So the same thing, nucleophilic attack, kicking it off, alkoxide, this gets protonated by the hydronium. This generates a tertiary alcohol. I'm not showing you the rest of the mechanism because I showed you 2 slides ago. So if we do this, we're going to get, right, nucleophilic attack right here, right? Electrons go up. This will generate the alkoxide version of it, and then it'll get protonated over here to generate the ethynyl cyclohexanol. So let's do a problem. Show how you would synthesize the following compound, beginning with acetylene and any additional necessary reagents. So here's the molecule. This is what you're going to start off with. So the first thing is you're going to need to add 2 groups of this onto acetylene, right? This part and this part. So they haven't shown you how to make this, but essentially what you're going to do is have acetylene. So I'm going to just show the triple bond. Do Na sodium amide, right? And step 1, and then react that with CH3CH2Br, right? So this will deprotonate to generate this product here. And then from here, you do another equivalence of sodium amide. This will generate the alkyne that's deprotonated, and then you reacted with the other half, which is over here, as an aldehyde. This will attack, kick off the oxygen, electrons to the oxygen from the alkoxide, but then that gets protonated with H3O, generating your product. So you can generate or produce alkynes by elimination reactions. So removal of 2 molecules of HX from a vicinal or geminal dihalide produces alkynes. You can do dehydrohalogenation of a geminal or vicinal dihalide to get a vinyl halide. And under strongly basic conditions, you can have a second dehydrohalogenation occur to form the alkyne. So let's look at elimination reactions in a bit more detail. Here's a vicinal and here's a geminal dihalide. So in the presence of base, you can have one equivalence of HX being removed to generate the vinyl halide. So I'm going to say base, right? So you're going to have base, negative charge, pluck off, right? And then kick out the halide. Then you can do another equivalence of base. So let's draw it in red. Base, negative electrons. So you can have that happen where, again, and this process is slow, but then you generate your alkyne. Same thing with the geminal. Again, in this case, you have base. We'll take one of the hydrogens, kick off the halide, and then you can have your second equivalence of base. Doing the same thing and kicking it off, generating your alkyne. So in terms of the types of base that you want to use molten KOH or alcoholic KOH at hot temperatures. If you do that, that favors the formation of internal alkynes. Sodium amide at 150 degrees, followed by water, favors terminal alkynes. So that expressed in actually a picture is shown over here. Here's your alkene. If you take potassium hydroxide at high temperatures, this will generate the internal alkyne. But if you use sodium amide at high temperatures at 150 and then add water, this will generate your terminal alkyne. Addition reaction. So we can take an alkyne reacted with a molecule that has a sigma bond, and that can come right on top and form 2 sigma bonds. You can add another equivalence of it, and then you'll have more being added so that you completely go from triple bond to single bond. Similar to addition of alkenes, pi bonds becomes 2 sigma bonds, usually exothermic, and 1 or 2 molecules may be added. So as an example, here's catalytic hydrogenation, which we talked about before, of alkynes. Here's your alkyne in the presence of 2 equivalents of H2, palladium, platinum, or nickel. You get full reduction from the triple bond to the single bond. So 2 molecules of hydrogen can add across the triple bond to form the corresponding alkane, and you need either of these catalysts. Under these conditions, the alkyne will be completely reduced. The alkene intermediate can't be isolated. You can do hydrogenation with Lindlar's catalyst, and this is something that you're going to have to memorize in terms of what the reagents are for Lindlar catalyst. It's hydrogen in the presence of palladium barium sulfate in quinoline and methanol. You can take an alkyne under the Lindlar catalyst, it will go to only one equivalence reduction, and it will generate a cis alkyne. So the hydrogen will come on one face, either top or bottom, but will generate a cis. So here, some little details. Catalyst, the catalyst used for the hydrogenation reaction is partially deactivated or poisoned. Catalyst used is known as Lindlar's catalyst. It's essentially composed of powdered barium sulfate coated with palladium poisoned with quinoline, and the reaction produced alkenes with, really critical, cis stereochemistry. Here's your mechanism in which you have hydrogen on the palladium catalyst, and so you have the C, triple bond C, coming down on one side, as a result forming the bonds and generating the cis. So the substrate and the hydrogen and the alkyne have to be adsorbed on the catalyst for the reaction to occur. Once adsorbed, the hydrogen adds to the same side of the product, giving cis, again, cis stereochemistry. Okay, so we're going to end here.